Manually computing the least squares regression line. Recall, the least squared criterion attempts to minimize the sum of the squared difference between the observed value of the dependent variable and the estimated value of the dependent variable using our regression equation. The parameters shown on this slide minimize the least squared criterion. Although the parameters in the equations for computing these parameters look exceptionally difficult to compute, we will show you how to set up the appropriate table to easily compute these measures. Ultimately, we use this equation to compute our B1, this equation to compute B0, and our ultimate goal is to set up the least squared regression equation y hat equals the computed value of B0 plus our computed value of B1 times x. In order to compute the parameters shown on the previous slide, you should always begin by setting up a table as shown on this slide. In the first column, you should place all of your independent variable values. In the second column, you should place their corresponding dependent variable values. In the third column, you should set up the column heading for x squared. And in our fourth column, you should set up the column heading for x times y. Let's insert the data into the first two columns for our example 3 problem. Now in the third column, you should square each x value for the row and place that squared value here in the third column. So first we should square 69 and place the value here. In the second row, we should square 67 and place the value here. We should do this for all of our x values shown on the chart. $72 squared is equal to 5,184, so we place that value here in the third column. In our last column, we should take each data pair for the row and multiply the x and the y value and place that product here. So first, we would say 69 times 9.5 and place the value here. And in the second row, we would say 67 times 8.5 and place the value here. We should do this for all of our rows. If we do this, your last column should contain these values. For example, 69 times 9.5 is 655.5. After filling in all of these columns, you should sum each of the columns and place that sum in the last row. So here the sum of our x values is 689. The sum of our y values is 98. The sum of our x squared values is 47,565. And the sum of our xy values is 6,800. Next, you should take the average of the first two columns. So you should compute your average x value and your average y value. Once you have completed this table, you will have all of the measures that you need in order to compute your B1 and your B0 values. Recall our formula for computing B1. It's equal to the summation of x times y, which on the previous slide is 6,800, minus the summation of x, which is 689, times the summation of y, which is 98, divided by n, which is 10. All of this should be divided by the summation of x squared. You should recall from the previous slide, the summation of x squared is the sum of the third column. This value is 47,565 minus the summation of x. The summation of x on the previous slide is 689, and then you square that sum. Make sure that you do not confuse the summation of x squared, where you square your x values first and then sum them, and this here, where you sum all of your x values first and then you square the sum. This first measure is the third column summed, and this one is the sum of the first column, and then you square that value. But it's divided by n, which for our problem is 10. I strongly suggest that you compute the top part first and get a value, and then compute your denominator and write down your value. But ultimately, our value for B1 in this problem is 0.5145. Our B0 value is equal to our average y value, which on the previous slide is 9.8, minus the value that we computed for B1 here, which is 0.515. I rounded it off to 3 decimal place positions there, times our average x value, which on the previous slide is 68.9. If we calculate this, we'll obtain that B0 is equal to negative 25.65. Therefore, plugging our B0 value into our regression equation, which recall is y hat equals B0, which for us is negative 25.65, plus B1, which we computed to be 0.5145, or we could have rounded this to 0.515 like we did above, times x. So this analysis allowed us to obtain a least squared regression equation which relates a person's shoe size, which is our dependent variable, to a person's height. Using this equation, if a person is 5 feet tall and we recorded all of our heights in terms of inches, so that's x, our height, equal to 60 inches, then I would estimate their shoe size to be B0 plus B1 times x equals 60, or in this case 5.22. So I would estimate someone's shoe size to be 5.22, and we generally round that up to a 5.5 shoe size. Now let's practice computing a regression equation for another example. Suppose we want to know the linear relationship between the average hourly temperature and the weekly fuel consumption. To explore this relationship, data was collected over an 8-week period. The data is shown in this slide. So here, our x variable, or our independent variable, is the temperature. And we say that the fuel consumption depends upon the temperature. Therefore, our y value is the fuel consumption. Now let's develop a least squared regression line for this problem. We begin by setting up our table and placing all of our x values in the first column, our y values in the second column, setting up the column heading x squared for the third column, and the column heading xy for the fourth column. Next, we fill in our x squared values for each row. 28 squared, 32.5 squared is 1056.25. We continue this for all of our rows. Next, we fill in our last column by taking the product of each XY data pair. 28 times 12.4 equals 347.2. 28 times 11.7 equals 327.6. And we do this for all of our data pairs in order to complete the last column. Next, we sum all of our columns, and then we take the average of our first two columns in order to compute the average x value and then the average y value. Now that the table is complete, we can begin filling in everything that we need to compute our B1 and B0 values. According to the equation for B1, B1 is equal to the summation of xy, which is 3,413.11, minus the summation of x, which according to the table is 351.8, times the summation of y, which is 81.7, divided by n, which is 8. We have 8 data pairs for this problem. All of this divided by the summation of x squared, which is the third column on our table, 16,874.76, minus the summation of x, which is 351.8 quantity squared, divided by n, our number of data pairs, which is 8. If we compute the numerator for this problem, we obtain negative 179.6475. If we compute the denominator, we obtain 1,404.355. Therefore, our B1 value is equal to negative 0.1279. Our B0 value is equal to y bar, which according to the previous slide is 10.21, minus our B0 value, which is negative 0.1279, times 44. Recall that the two negatives together become positive, and our B0 value should be equal to 15.84. Now that we have computed B0 and B1, we can fill these two values into our least squared regression equation. This equation is y hat equals B0, which for our case is 15.84, plus B1. So plus a negative 0.1279 is just minus 0.1279 times x. So for this problem, if our x value is equal to 40, we can estimate that our y value would be equal to 15.84 minus 0.1279 times an x value, which is 40. This gives us a y estimate of 10.72 as our fuel consumption when the temperature is 40 degrees. Now let's get some hands-on practice computing a least squared regression equation. Read Auto periodically has a special week-long sale. As part of the advertising campaign, Reed runs one or more television commercials during the weekend preceding the sale. Data from a sample of 5 previous sales are shown on this slide. Let's use this data in order to compute the least squared regression equation. You should pause the video at this time and try to complete this problem. You should have set up a table with your x values, our y values, your x squared values, and your x times y data pairs. You should have summed up all of your columns and computed the average for the first 2 columns, as shown on this slide. Next, you should have used our equations for computing B1 and B2. B1 is equal to the sum of xy, which is 220 for this problem, minus the sum of x, which is 10, times the sum of y, which is 100, divided by 5. All of this should be divided by the summation of x squared, which is 24, minus the summation of x, which is 10, squared, divided by n, which again in our case is 5 since we have 5 data pairs. You should have computed B1 to be equal to 5. Your B0 value should be y bar, which is 20, minus our B1 value, which was 5, times x bar, which is 2. Your B0 value should be 10. Therefore, the estimated regression equation for this problem should be y hat equals B0, which for us is 10, plus B1, which is 5, times x.